Well, I'm going to charge on into talking a little bit about climate change and how it affects seaweeds. Can't have to start with temperature because that is such a huge effect both terrestrially and marine environments. So perhaps you've seen this from 1951 to 1980. They're trying to show the change from average. So you take an average between those two dates, and then you look at how year by year it has deviated from that average. Look what has happened in this millennium. It had actually started here. It's just gone up. And we're aware of that. We can see the signal of El Nino years here, that were super hot, and La Nina years for that matter, where things were cooler. So temperature is not smooth, but it is without a doubt increasing globally. So this is air temperature, and the ocean follows. Look at this macrocystis plant during the 1984 El Nino. This is what happens in warm water to kelps. They lose their tissue. They cannot get enough nitrogen out of the water to replenish their tissues. So they fade away. Once these blades are gone, there's not enough photosynthesis in the floats and the stipes, and they tend to lose buoyancy from the floats and fall to the bottom and are eaten. So this is what happens in Southern California during a very, very severe El Nino year. And we have had more severe ones since then. Actually, I first started diving in Southern California in the early 80s, and I thought El Nino conditions were what it was like. And then when the colder water came back, I saw the ocean bloom. It was really very wonderful, which reminds me the fact that what we see now is not what it's always been. There's an idea called sliding baselines. We establish baselines by saying, this is what I saw, and look how it's changed now. But what we saw is the end of another baseline that was different in the past. So this is particularly applied to things like game fish. They used to be huge, they used to be big. Now we don't even expect that. We expect them to be harder to get and smaller because we didn't know what it was like in the past. So I want you to bear that in mind with all the news today. All we have is what we have, all we know is what we have in our own history. We're trying to backcast, and I'll talk about this a little bit, to understand what it was before we were measuring things so that our baseline will be more accurate. Let me give you an example of a Galapagos seaweed. I went to the Galapagos to collect endemic seaweeds that had never been seen since they were described, because the 1984 El Nino in the Galapagos was so severe, it's so near the equator, that the warm water went right down into the subtidal, very, very deep. And a lot of plants and animals were deeply, deeply affected by this warming trend, the same one that bleached the macrocystis. So Bifurcaria galapagensis is a rockweed. You know some rockweeds. Here it is, a little skinny thing. This is what it used to do on those black volcanic shores. A picture from 1974. It covered the shorelines. Now it is gone. So one of our missions when we went there was to look for Bifurcaria, and we did not see it. We didn't go to every place and every island, but we went to a lot. So this is one of the few seaweeds. There's one Australian seaweed and this one that has been actually considered most likely extinct due to climate change. And it has been added as such to the International Union of Conservation Red List in 2007 when we did our work. And we looked at we found quite a few just by going down and looking. We found quite a few other endemic seaweeds that are not extinct, but some are rarer. This is a deep water kelp that occurs very near the equator. So it's a kelp that is dependent on cold water, and it gets it down deep. Used to be very common in Academy Bay, which is where the town is, the most accessible place in the Galapagos. You can see it's an Eisenia. It's related to our Eisenia arborea. It has patches of reproductive zoospores. This is an old specimen. This is actually the type specimen that William Randolph Taylor collected and named. So we went searching for this kelp. We had to go down deep to find it, and we found it. It was there, but not as extensively as it used to be, and probably deeper than it used to be. But it has not gone extinct. It has run away to deeper waters. So this might be a story for other kelps that can get enough light in deeper water to persist, drawing on the nitrogen in that colder water. So not every species is the same. Bifurcaria seems to be gone and hasn't recovered yet. This thing may be coming back unless we get more and more severe El Niños or heat waves at the equator. Let's see, the Gulf Stream. Yeah, the Gulf Stream comes right up here. Thank you very much. So ocean currents are strongly affected by climate change. And it's because they're part of the hydrological cycle intimately connected to the atmosphere. So anything that's happening in the atmosphere is going to affect the ocean, and anything affecting the ocean is going to affect the movement of these great currents on a global scale like this. So here's the Kuroshio current, which is a warm current that comes from here and bathes southern Korea and Japan. And it's about the same as California here. That's why we have so many species in common in Southern California and Southern Japan, because it's a very similar climate. Similarly, there's cold currents that come down and keep Northern California, here's the California current, cool, and then goes offshore to form these great gyres, including the garbage patch. There's the equatorial currents. Each ocean basin has its set of both warm and cold currents that play off each other and have been established for a very long time, ever since the continents got to be where they are today. But these currents are changing. And that's one of the most frightening things for oceanographers, to realize that the things that we've always taken for granted are mutable. They will change. And if the Gulf Stream weakens, if the California current weakens, there'll be more warm water and possibly more, certainly less nitrogen. So ocean currents are something to keep your eye on. Even our Antarctic circumpolar current, which goes all the way around the world, may be changing as a result of these icebergs calving off and changing the salinity of the water. So this is big, huge, and strongly affects our nearshore environments, including kelp beds and other seaweeds. So looking at our own place here, here's the California current coming down, cold water, and the countercurrent is on the surface in the winter, but it's subsurface in the summer. So the summers remain cold here, and San Franciscans are cold. But if the California current weakens, this countercurrent here could strengthen, bringing more warmer water up our coast and really changing year-round conditions here. So remember this picture here, the upwelling regions that are very cold that keep our kelp so happy in the northern coast upwelling is rarer in the southern, but enough to keep macrocystis and other kelps near shore happy. But this orange, and especially this green Central Pacific water here that comes to our coast, could be more plentiful, and climate change may change the wind patterns enough to slow down upwelling in this, and the restitution of nitrogen in our nearshore waters. So all of this, all of it's connected. This is an interesting paper. I'm sorry I didn't put the reference on it, but our herbarium contributed specimens for this. They looked at the genus Gelidium, and they got our oldest species specimens and about 100 years worth of specimens of Gelidium. So here we see an upwelling index that has actually been measured by people ever since about 1946. We've been measuring this upwelling index. The reason we're measuring it is because the sardines crashed. Remember that in the Steinbeck sardines? Sardines crashed and people started worrying about ocean temperatures in 1946. The war was behind us and we started doing more oceanography with our ships. So here's what we know from data. But by using nitrogen isotopes in those Gelidium specimens, taking us all the way back to 1880, they backcasted nitrogen levels in the ocean. And there is slosh, you know, it's not a precise measure. It's not as precise as actually measuring nitrogen, but they were able to capture the sardine boom and what sustained the sardines and its crash by backcasting with nitrogen isotopes in seaweeds. And these are using old herbarium specimens. And that's a new frontier, a new technological frontier to try to understand our past so that our baseline is more accurate, so that we don't start here with our baseline, but start in the past. Everything is connected. Let's look at sea level. Just have a few more minutes. 18,000 years ago, the upper part of the world was locked in ice, the last glacial maximum. Here are the Farallones. They are a ridge inland. This is San Francisco. And these are the great rivers going down to the sea. The sea level was 120 meters lower and the shoreline was 19 miles out. So think of how our shoreline has changed in the last few thousand years, and it is going to change more. It has continually eroded in closer and closer, and that trend will continue. Storm surge and high tides magnify sea level rise. Floridians are concerned with this now, and we are becoming concerned as our cliffs crumble into the sea. 2010, 2050 projected high tide, 2100 projected high tide. It's all moving onshore. So sea level rise, and this work was done quite a while ago, and we're realizing that things are calving into the ocean and melting a lot faster than we expected. Greenland, Antarctica, the Arctic Ocean, etc. But the floodplains are getting higher and higher and higher every year, and the storm surge in the winters is further than the floodplain. So this is a future we coastal elites are looking at, seeing the sea level rise. And what happens to the intertidal zone? It's gone. It's gone. Or our cities become the intertidal and seaweeds, you know, grow in our windows. But this is probably not fantasy. Sea level rise is happening and faster than we thought. Huge implications for nearshore, both seaweeds and animals. And we can't not talk about ocean acidification, which is a very squirrely feeling for me. Ocean acidification, this is backcasting to 1750, 2005, forecasting to 2050, the ocean is going from alkaline to acid rapidly. These are surface waters. And as you can see, the near shores are strongly affected because of upwelling. Upwelling brings more acid to our waters. And of course, that acidification has negative effects on calcified species like the coral and algae, not to mention many, many mollusks and other phyla. So upwelling is the gift of nitrogen, but at the same time, it's bringing acidification to our shores. Very, very difficult to balance that in our heads. We've already seen the effect of ocean's acidification on raising oyster beds, juvenile oysters. The juveniles have tiny shells. They dissolve. People are having to think about that. A lot of the phytoplankton with calcified shells are dissolving. So upwelling brings both the benefit of nitrogen and, unfortunately, this. But once again, using this picture, let's go back and how long have our creatures lived and what have they seen in the last 1,200 million years? They've changed, though some of our fossils look an awful lot like they do now. So we have to comfort ourselves with an evolutionary perspective as we watch the library burn. Our seashores are changing rapidly, but we can't always see it. We don't see that acidification. The intertidal zone may be the most vulnerable habitat on our shores. The subtidal will also shift. Geographic range of seaweeds will surely change, and many of them will move from warmer waters in the south up north following the warm water trends. Subtidal kelp forests are likely to contract regionally, though we have not yet said that they've tipped to extinction. Effects of climate change on seaweeds are species specific, and so far, extinctions are rare. Questions?